My dear students, I am Dr. Neeraj Upadhyay, Assistant Professor of Dr. Hari Singh Gaur Vishwavidyalaya, again in front of you for delivering module number 3. In the last class, I taught you about general characteristics of D block elements with special reference to electronic configuration of elements of first, second and third transition series with general exceptions and their cause. We also learned about properties associated with the electronic configuration of elements like about metallic character, hardness, atomic volume and density, melting and boiling point, ionization energy, and about the reactivity of the elements of D block elements. In this class, we will learn about some special properties which you have not learnt during periodicity of the properties of these elements. Let's see about the general curiosity of the students which I have several times faced, which is good for learning any subject. Sir, I learned transition metals have variable oxidation states and variation in oxidation state is very large. I mean, transition metal has possible oxidation states from +2 to +7. Why it is so? Second question. Sir, I know transition metals are good catalysts, but we have several other elements in the periodic table and their compounds are available. What is special with transition metals? Transition metals and their salts are colored, while most of the S and P block elements and their compounds are colorless. What is special with the transition metals? Sir, why iron shows magnetic behavior if we put it in magnetic field? Dear students, you are lucky enough we will answer all these questions in this lecture only. In this module, we will learn to investigate and examine various chemical applications of transition metals and their compounds. We will also learn to observe general applications of catalytic and magnetic properties of transition metals in daily needs as an eye-opening for applying these concepts in other places. The prerequisite for this particular module is the basic understanding for periodicity in properties, molecular forces and redox behavior. So let's start the lecture with the variable oxidation states. As you know, oxidation state is the combining capacity of an element in the covalent molecule on the basis of expected electron withdrawn by the most electronegative element of the compound. For example, in HCl, chlorine being more electronegative and needs 1 electron to fulfill its need to complete the octet and therefore will have oxidation state -1. Because of -1 oxidation state of chlorine and need of neutral molecule, that is overall charge of HCl is 0, the oxidation state of hydrogen will be +1. Let oxidation state of hydrogen in hydrogen chloride is X. Chlorine has oxidation state -1. For the condition of neutrality of HCl, the sum of oxidation state of hydrogen and chlorine should be 0. It means X plus -1 is equal to 0 and therefore X is equal to +1. For finding oxidation states of more complex examples, there are some operational rules. I expect you have already learned those rules in the previous chapters, like in oxidation reduction, which was the part of intermediate and BSc first semester course. The chapter is also a prerequisite for learning this module. So please revise the chapter before proceeding. I have a question for you. Why elements are charged or get positive or negative oxidation state on it? Please answer the question. This is because all elements try to get stability, and for that they try to attain nearest inert gas configuration. In case of transition elements, even after losing 2 valence electrons, the ion do not get inert gas configuration. For example, manganese after losing 2 valence electron do not get inert gas configuration with 24 remaining electrons. The inert gas configuration can only be achieved by removal of 5 more electrons. Removal of each electrons from manganese either in ground or in ionized state, require some energy. It is therefore the possible oxidation state of manganese is from +2 to +7. Like manganese, all transition elements show variable oxidation states which can be diagrammatically shown like this. Scandium, on removal of all of 3 electrons, attain inert gas configuration. Therefore, shows only oxidation state, that is +3. While titanium can have the oxidation state +2, +3 or +4. The trend goes on increasing manner till the element manganese attain a total of 5 unpaired electrons in d sublevel, and therefore it has variable oxidation state from +2 to +7. Iron, having only 4 unpaired electrons, may have variable oxidation state from +2 to +6. This is because oxidation state does not only depend on maximum possible charge on central metal but is also a representative of binding capacity of the element. Iron, being a small size metal, can handle of framing covalent bond with 4 unpaired electrons, and therefore in addition of +2 oxidation state, it can show +3 to +6 oxidation state only. In a similar manner, trend in oxidation state vary from cobalt to zinc. Copper, being an exception, show +1 oxidation state in addition to +2 and +3 as a result of extra stability of d sublevel. But it doesn't mean that +8 oxidation state is not possible. With increase in size of central metal ion, +8 oxidation state is also possible, like in the case of ruthenium tetroxide or osmium tetroxide. Catalyst is a compound that accelerates a chemical reaction without undergoing net chemical change in it. In general, catalysts participate in a chemical reaction by framing an unstable intermediate that can easily decompose to form product and regenerating itself. By this process, reaction goes through a new path having completely low activation barrier, and therefore rate of reaction enhances. A general chemical reaction involving a catalyst is shown here, where M and L are the 2 reactants and interact with catalyst C to form an intermediate called MLC, which ultimately degrade to form product P and regenerate catalyst C. There is no net change in the concentration of catalyst C during the process, and therefore there is no net chemical change of catalyst C. Transition metals and their compounds are having variable oxidation state that favors of forming unstable intermediates. The large surface area of transition metals make it good adsorbent, where the reactants get adsorbed and come closer for further reaction. For example, nickel is a catalyst known for hydrogenation of alkene. In some cases, both alkene and hydrogen are gases where their collisions are very difficult. They both or one can adsorb over nickel surface on account of its large surface area to increase the rate of collision between the 2 reactants that ultimately enhances rate of the reaction. Similarly, hydrogenation of alkene using Wilkinson's catalyst, which is RHCl3, where L is PPH3, is done because of both variable oxidation state of rhodium and large surface area of RHCl PPH3 The first step involves oxidative addition of hydrogen. Oxidative addition is a process in which coordination number and oxidation state, they both are increased by a value of +2. Second step involves coordination of alkene to rhodium, by which both alkene and hydrogen comes closer. In the third step, insertion of hydrogen on alkene occurs, followed by the reductive elimination of alkane. The reductive elimination involves decrease in the coordination number and oxidation state by the value of 2. So this is the process by which a product alkane forms through alkene and hydrogen, in which your catalyst is regenerated. In general life, you might have heard about catalytic converter in a car. On burning of fuel, toxic gases generates. Catalytic converter converts these toxic gases into comparably less toxic gas before the exhaust. In the process, you need both the oxidation and reduction procedures. Palladium is used as an oxidation catalyst, rhodium is used as a reduction catalyst, and platinum roles as both oxidation and reduction catalyst. Now, since we are learning about the redox processes, let's move towards the standard electrode potential and the reducing properties of the elements of transition series. Here is a table that comprises of standard reduction potential of the elements of first transition series. As obtained from the table, elements of first transition series except copper have lower reduction potential than standard hydrogen electrode potential, which is taken as 0 as a convention. It is therefore most of these transition metals oxidize easily. When they react with acid, they are expected to ionize, and this is one of the major reasons behind the corrosion of metals. Now in actual practice, this reduction is very slow, and sometimes a protective layer of metal oxides saves further oxidation of the metal. For example, chromium is having reduction potential minus 0.74 volt, but it is almost inert against acid because of presence of resistant layer of inert chromium oxide. Because of their low reduction potential, all transition metals easily release electrons and reduce other molecules. It is therefore transition metals are good reducing agent. However, they are not as good reducing agent as alkali and alkaline earth metals. The reduction of copper is higher than hydrogen, and therefore copper doesn't easily oxidize and become inert against acid. Let's move towards the Latimer diagram of your course. Elements of transition series show variable oxidation state. It is therefore all elements in their transformation from one oxidation state to other have a different reduction potential. For example, manganese can have oxidation state between +2 to +7. So, the transformation of Mn +7 to Mn +4 will be different than the transformation of Mn +7 to Mn +2. Reduction potential is an important tool which is deciding factor for proceeding of any redox reaction. It is therefore we need to have reduction potentials for almost all such transformations. A Latimer diagram of an element is basically a summary of reduction potential of that element in its various oxidation states. Let's first see the Latimer diagram for manganese in acidic medium and then discuss about the outcomes. As you know, free energy is a state function and doesn't depend on the followed path. Therefore, free energy for the transformation of MnO4 minus to MnO2 is basically sum of transformation of MnO4 minus to MnO4 minus, MnO4 minus to MnO4 minus, and MnO4 minus to MnO2. So, delta Ga is equal to the sum of delta G1, delta G2 and delta G3. You also know that delta G is equal to minus NFE, where N is the number of electrons involved in the reduction process, E is the reduction potential, and F is a constant called Faraday, which is equal to 96500 Coulomb. So, if N1, N2 and N3 are the number of electrons and E1, E2 and E3 are the reduction potential involved in the steps 1, 2 and 3 respectively of the Latimer diagram shown here on the screen. If Na and Ea are the number of electrons and reduction potential involved in direct transformation of MnO4- to MnO2 in acidic medium, then minus NaFEA should be equal to minus N1FE1 plus minus N2FE2 plus minus N3FE3, and therefore Ea should be equal to N1E1 plus N2E2 plus N3E3 divided by Na, or Ea should be basically a sum of Nei by N, where N1 and E1 are the number of electrons and the reduction potentials involved in step 1, and N is the total number of electrons involved in a particular transformation for which we want to calculate the reduction potential. Again, I have a question for you. Why in acidic medium Mn+7 prefers to convert into Mn+4? This is the work for you. I can only give you a hint that the transformation that would have maximum value of reduction potential will be preferred. So, I'll see your work on that during the discussion thread. Now, let's move towards the color of transition metals and their compounds. Unlike compounds of alkali and alkaline earth metals, most of the compounds of transition metals are colored. Let's discuss first the science behind the color of a compound. Before discussing behind the cause of color in transition metals and their complexes, let's first discuss about the cause of color in any compound. Light is framed by electromagnetic radiations, the spectrum of which broadly divided into 8 bands and are gamma radiation, X-ray radiations, ultraviolet radiations, visible radiations, infrared radiation, microwave radiations and radio wave radiations. Within these 7 bands, our eye can only see the visible zone, which comprises between 380 nanometer to 760 nanometer. The sum of the all wavelengths of visible zone frame a white color output, means white color is an output of sum of all the radiations between wavelengths of 380 nanometer to 760 nanometer. Even if a single wavelength of light becomes absent between this zone, the net result will not be white but of another color. When light falls onto a matter or a compound, the light can be absorbed or can be transmitted out. When ultraviolet or visible light is absorbed by the compound, electronic transition takes place. So, absorbed light causes excitation of electron from ground energy level to excited energy level. Since all energy levels are quantized, it is therefore a fixed wavelength of energy will be absorbed and rest all wavelength of light will be transmitted out. A compound will be colored only if after absorption of light by it, the compound transmit energy in the visible zone only. In most of the cases, all the compounds of alkali metals and alkali earth metals, the energy gap between their ground and excited state is higher and they can absorb fixed wavelength of energy in ultraviolet region, which ultimately doesn't affect the visible zone, and therefore compounds of alkali and alkaline earth metal look white in color. On the contrary, energy absorbed by the compounds of D and F block elements is in visible region, and therefore resultant transmitted light miss one or more wavelength from visible zone. The reason behind this absorption in visible zone is DD transition and charge transfer, the mechanism of which we will learn in module number 15. I have a question for you. Why blood is red in color? This is because of hemoglobin in your blood. Hemoglobin contains heme, which when attaches oxygen to it, it becomes oxyhemoglobin. This oxyhemoglobin, after absorbing green-blue light, transmit red color, and this is why blood is red in color. Mind it, deoxyhemoglobin is not exactly red in color. Instead, it is a purplish yellow. Now let's move towards the magnetic behavior of elements of transition metals and their compounds. Unlike other metals, transition metals generate magnetic field, and some of the compounds behave like permanent magnet. Let's first discuss about the origin of magnetic field and then correlate them with the transition metals. Charged particles on moving, when frame a loop, it creates magnetic field. This you all know. Magnetic field is a vector quantity and the direction of the field is governed by the right hand thumb rule. That is, if direction of current is pointing by your right hand thumb as shown in the figure, then the direction of the magnetic field will be circling in the direction of the rest of your finger as shown in the diagram. Current is generated by movement of electrons. In an atom, we have several electrons, and therefore, because of movement of this current in a loop, magnetic field originates. So the origin of the magnetic field are different. In an atom, the magnetic field originates by the spin of the electron or by its angular momentum or the combination of both. A spinning electron around its own axis creates a circular loop having infinitesimally small diameter, and the magnitude of magnetic field created by all the electrons would be same as far as charge and velocity of electrons remain same. So, magnetic field created by the electrons having opposite spins cancel out each other. It is therefore only unpaired electrons used to create magnetic field. Most of the transition metals have unpaired d electrons which generates magnetic field. Details on the magnitude of magnetic moment of the transition metals we will learn later in this course. The magnetic field associated with our Earth is believed to be because of metal ions flowing in the core of Earth. We call this field as geomagnetic field, which interacts with the solar wind and helps us in saving from charged particle emanating from the sun. Let's summarize the whole learning. Unlike alkali and alkaline earth metals, transition metals have variable oxidation states which produce diverse chemistry and redox behavior. The redox behavior of these elements and their ionic form is interesting to learn. Because of variable oxidation states and large surface area, transition metals and their compounds act as good catalyst. The reduction potential of most of the transition metals is negative and therefore most of them act as good reducing agent. The redox behavior of an element or compound in a specific medium is represented in a Latimer diagram, which is used to find most probable transformations during chemical reaction in a specific medium, that is in acidic or basic medium. Unlike elements of S and P block, most of transition metals and their compounds are colored. Most of the transition metals have unpaired electrons and therefore they create magnetic field. I hope you must have enjoyed the lecture. Be prepared for the next class. There you will learn about valence bond theory for formation of coordination compound. Thank you very much for listening me patiently.